Welcome. Today we are diving deep into real numbers and the power of exponents. Master Surds, rationalize denominators, and unlock the laws of exponents that will transform how you solve complex equations. Let's get started. When we add or subtract irrational numbers, the result can be either rational or irrational. Let's see what determines this. First example, root 2 plus root 2. When we combine like irrationals, we get 2 root 2, which is still irrational. Now look at this, root 2 plus 1 added to 2 minus root 2. When we simplify, the irrational parts cancel out. Root 2 minus root 2 is 0. 1 plus 2 is 3. The result is 3, which is rational. The key rule. If irrational parts cancel completely, the result is rational. If they remain, the result is irrational. Rationalizing the denominator means removing radicals from the bottom of a fraction. We do this for two reasons. It simplifies calculations and it's the standard mathematical form. For a simple case, like 1 over root 2, we multiply both numerator and denominator by root 2. The numerator becomes root 2, the denominator becomes root 2 times root 2, which equals 2. For binomial denominators like root 3 plus root 2, we use the conjugate. The conjugate swaps the sign between terms. We multiply numerator and denominator by the conjugate. Root 3 minus root 2. The numerator is root 3 minus root 2. For the denominator, we use the difference of squares formula. A plus b times a minus b equals a squared minus b squared. The denominator simplifies to 1. So the final answer is simply root 3 minus root 2. The general pattern works for 1 over a plus b root c multiplied by the conjugate a minus b root c, and the denominator becomes a squared minus b squared c. Simplifying surds makes expressions cleaner and easier to work with. There are three key techniques: combining like surds, splitting surds, and simplifying nested radicals. First, combining like surds. These are surds with the same radicand, just like combining like terms in algebra. But what if we have surds with different radicands like 3 root 5 plus root 20? First, we need to simplify root 20. Root 20 equals root 4 times root 5. Root 4 is 2, so root 20 equals 2 root 5. Now we can combine 3 root 5 plus 2 root 5 equals 5 root 5. The rule for splitting surds: root of a product equals the product of roots. Root a times b equals root a times root b. Let's look at nested radicals. Root of root 8. We can simplify this by working from the inside out. Root 8 is 2 root 2. Then we take the square root of 2 root 2. This can be rewritten using exponents. 8 to the power of 1/4, which is the fourth root of 8. The laws of exponents are the foundation for all algebraic manipulation. Let's recap the four most important ones. Law 1. When multiplying powers with the same base, we add the exponents. A to the m times a to the n equals a to the m plus n. Example, 2 cubed times 2 squared, that's 2 to the 3 plus 2, which is 2 to the 5th, or 32. Law 2. When raising a power to a power, we multiply the exponents. A to the m all to the n equals a to the m times n. Example, 3 squared all squared, that's 3 to the 2 times 2, which is 3 to the 4th, or 81. Law 3. When dividing powers with the same base, we subtract the exponents. A to the m divided by a to the n equals a to the m minus n. Example, 5 to the 5th divided by 5 cubed, that's 5 to the 5 minus 3, which is 5 squared, or 25. Law 4. Any non-zero number to the power of 0 equals 1. a to the 0 equals 1. This works for any base except 0 itself. 10 to the 0 is 1, x to the 0 is 1, even a half to the 0 is 1. Negative exponents might seem confusing, but there's a simple rule: a to the negative n equals 1 over a to the n. Why does this work? Let's use the quotient rule: a to the m divided by a to the n equals a to the m minus n. Let's try a concrete example: 2 to the negative 3. X to the negative 2 becomes 1 over x squared. Now, here's a very common mistake. Some students think a to the negative n means negative a to the n. This is wrong. The negative sign in the exponent does not move to the answer. It only tells us to take the reciprocal. Another mistake. Some students try to simplify by moving only part of the expression. For example, they might write x to the negative 2 over y to the 3 as x over y to the 3, forgetting to flip x. You must apply the rule to every term with a negative exponent. Let me show you a cleaner example. The key is negative exponent means reciprocal. Always flip the base to the denominator and make the exponent positive. Rational exponents are exponents that are fractions. They're the bridge between radicals and exponents, and they follow the same laws we learned earlier. The key rule: a to the power of p over q equals the quotated root of a to the power of p. Let's start simple. A to the 1/2. Specific example: 2 to the 1/2 is the square root of 2. Now try x to the 3/2. The denominator is 2, so we take a square root. The numerator is 3, so we raise to the power 3. 8 to the 2/3. Denominator is 3, numerator is 2. Converting from radical form to exponent form works the same way in reverse. The root index becomes the denominator and any exponent inside becomes the numerator. The big advantage of rational exponent form is that you can use all the exponent laws. Let me show you. This is much cleaner than trying to multiply square roots and cube roots directly. Rational exponents let us use algebra. Now we combine everything. These mixed problems use all the rules we've learned. The key is to work systematically and apply one rule at a time. Problem 1. Simplify the square root of 16x to the 4th y squared multiplied by root 3xy. The first radical, root 16, is 4, root x to the 4th is x squared, root y squared is y. So the first radical is 4x squared y. The second radical cannot be simplified further. It stays as root of 3xy. Multiplying them together, 4x squared y times root of 3xy. Problem 2. Simplify. Open bracket 2x cubed y to the negative 2 divided by 4x to the negative 1y. Close bracket all squared. Inside the bracket, divide the coefficients first. 2 divided by 4 is 1/2. For x terms, use the quotient rule. X cubed divided by x to the negative 1 is x to the 3 minus negative 1, which is x to the 4. For y terms, y to the negative 2 divided by y is y to the negative 2 minus 1, which is y to the negative 3. Inside the bracket simplifies to 1/2 x to the 4th over y cubed. Now apply the outer exponent 2. This means we square everything. Final answer: x to the 8th over 4 y to the 6th. Problem 3. Simplify. Root of root 32 divided by 2 to the negative 1/2. 32 is 2 to the 5th. So 32 to the 1/4 is 2 to the 5th times 1/4, which is 2 to the 5/4. For the denominator, 2 to the negative 1/2 is 1 over 2 to the 1/2, or 1 over root 2. Now divide. 2 to the 5/4 divided by 2 to the negative 1/2. Using the quotient rule, we subtract exponents. Add the exponents. 5/4 plus 1/2. 1/2 is 2/4. So 5/4 plus 2/4 is 7/4. We can also write this as the fourth root of 2 to the 7th or the fourth root of 128. These problems all use the same core idea. Work systematically, apply one rule at a time, and keep simplifying until you can't anymore. You've just mastered the fundamentals of real numbers and exponent laws. If this video helped you understand these concepts, please like and subscribe for more mathematics lessons. Drop a comment below if you have questions or want to see more topics covered. Thanks for watching and see you in the next lesson.